of equations and solving it. And what about what that means? So let's start out with just a couple of practice graphing problems. So if we graph these two different equations, we have to find the y-intercept, then use the slope to find other points, and the same with the other equation as well. So I've already graphed a couple of points, and they would look something like this. So you've got your -5 y-intercept, and then a slope of down 1 over 2, down 1 over 2. And then this next one, you've got a y-intercept of 2, and a slope of up 3 and over 1. So if I go ahead and graph a line in between those two, I notice, wow, they actually intersect. And where do they intersect? Well, right here at this big bright yellow point. So that's significant, and that's kind of what we're going to focus on today in our lesson. So when we talk about solving systems of equations, we're actually talking about two or more equations that intersect with each other when you graph them. And so we're trying to find that x and y value that is the place where they cross. So they have the same x and y value at that one common point. So when you're solving a system of equations by graphing, both equations must be written as y equals mx plus b. You graph both lines on the same graph and find the point where they cross, the x and y coordinate where they cross. That is the x and y value that works for both equations. So here's kind of a graphic example of what we're talking about. So let's try a few of these. Before we do our first one, however, we need to understand that if I graph a couple of equations and the lines are parallel, that means that there's no solution. They never do intersect. Now, on the other hand, if the lines do intersect in one point, that's just one solution, and we get to name what that solution is based on what the coordinates are. Once in a while, we find out that when we graph two lines, that we actually had the same two equations. They may have been written a little more differently, so you couldn't quite tell they were different. But once you graph them, you find out that they are the same line. And so if you have that case, you get the infinite number of solutions because they touch everywhere. Okay, so there's the bell to tell us to start to graph a few of these, and we only have a few minutes. So the first one, we start at +2. So we go up to +2, make a dot, and then from there we go up 1 and over 2, up 1 over 2, up 1 over 2. I'm also going to go down 1 and back 2 because I want to make sure I have plenty of line here, because you never know where these are going to intersect. Now let's look at the second equation. We go down to our y-intercept of -1, and we have a slope of down 1 over 1, down 1 over 1, down 1 over 1. Well, I'm going to go up 1 and back 1, up 1 and back 1. Oh my goodness, when I did that, I happened to stumble across where they intersect. So it looks like they come through like this, and this comes through like this. So when you look at your intersection point, which is right there, that happens to be -2, 1. -2, 1. And that would be considered the solution to that system of equations. All right, let's try another one. Here's one of those unusual ones of x equals -4. So we go to 1, 2, 3, 4. There's where x is -4, and we know that we're going to be talking about all the points up and down this line because every one of them has an x value of -4. Let's look at our second one. We have a y value of 2, or y-intercept of 2, and then our slope is up 3 and over 2. Up 3 over 2, and I'm going to go down 3 and back 2, down 3 and back 2. And sometimes by doing several points, you can actually find the intersection of these graphs rather nicely, because you can see that they cross right here. And that point would be -1, 2, 3, 4, -4, comma, and then down 1, 2, 3, 4. Oh, -4, -4 is where these two cross, so that would be their solution. All right, let's try another one. We've got 4x minus 4, so we start at 1, 2, 3, 4, -4. We have a slope of up 4 over 1, up 4 over 1. On our next one, we start at +1. We also have a slope of 1, 2, 3, 4 over 1, 1, 2, 3, 4 over 1. Wait just a minute, I'm thinking about this here. If I have the same slope, that means that my lines look like that, which means they're parallel. And if there's parallel, then that means that there's no solution. So that's one of those no solution problems, because the lines were parallel. All right, keep moving along here. I'm going to look at these slopes. A divided by 2 happens to be 4. So if I simplify that, I get 4x plus 3. Y equals 4x plus 3. Oh, well, if you look at that, we actually have the two identical equations. So if I was to graph the first one, I would have a y-intercept of 3, and then a slope of 1, 2, 3, 4 over 1, down to 3, 4, back 1. Both lines are going to come right through here, right on top of each other. So this is an example of a problem that has infinite solutions. And sometimes we just do this for short, because it's easier to write. So that one has infinite solutions. All right, now these two have different slopes, so I think we're going to get one unique solution. So on this first one, we go up to 1, 2, 3, 4 and make a dot. And then we have a slope of 1, 2, 3, 4 and over 1. And then we're going down 1, 2, 3, 4 and over 1. So there's that first one. Now the next one has a y-intercept of 3, 1, 2, 3, then a slope of up 2 over 1, up 2 over 1. All right, so let's go ahead and graph those. I'm going to grab a line and come right down through those. And you got to be careful how you graph them, because if your graph is inaccurate, then your solution could be inaccurate too. All right, let's make sure we graph that one properly. We went up to 4, came down 1, 2, 3, 4, and uh-oh. I've got to redo this first graph. So if you have to redo it, just go in there and get rid of your points. You might have to erase your arrow. So I've got to double check that. So I was supposed to start at 4, 1, 2, 3, 4, and then go down 1, 2, 3, 4 over 1. So when I come through here, where am I crossing? That's a pretty tricky place to see. Some of them are kind of tricky to find out where they're at. So you got to best estimate that. So it looks to me like it's somewhere around over about 0.3, because you're just over a little bit, and then up about 3.2, something like that. So that could happen as well. So you got to just estimate where, as close as you can, where it's at. Okay, let's do another one. We start out with a y-intercept of 2. Then we have a slope of down 1 over 2, down 1 over 2 more. All right, let's go ahead and put our arrow in there right now. So we got an arrow that comes through, looks like this. And what we should do is we should stretch that arrow out so that it goes quite a bit of distance in both directions. Okay, let's do the next one. We start out at -2, make a dot. and the slope on this one is down 1, 2, 3, 4, 5, and over 2, or up 1, 2, 3, 4, 5, and back 2. So like we mentioned before, sometimes graphing a couple of points will actually help you find the solution faster than just drawing the lines. But anyhow, there's the solution. So that would be negative 2, comma 3. Very nice. Okay, so that's what we're doing today is we're going to practice graphing a couple of linear equations, see where they cross. If they don't cross, there's no solution, or if they end up being the same line, there's infinite solutions. But if they just cross in one point, you're trying to name those, that x and y value where they cross. Thank you very much.